Okay, we've got, what do we got? Physical science tonight. It is Monday night, November 23rd. We're going to record this physical science module 6, Earth and the lithosphere. So let's get to it. I need to share my screen here for you guys. So let's figure that one out again. How do I do that? Share screen. There we go. All right, physical science students. So we're gonna roll through this entire module. We did a number of the labs last week in class, and so this week we're going to do all the material. Sit down, let's take us about 30 minutes. So grab yourself something nice like a glass of water. Remember talking about the hydrosphere last week. Now we're going to talk about the Earth and what's under it this week. We did experiment 6.2 and 6.3 in class. I'd like you to go back into your textbook and look at experiment 6.1. See if you can't do that at home for me this week. Talking about how sound waves travel. So look into that. It's an easy experiment you can do right at home. Try to do that for me this week. It's a good one. It's a fun one. Now, there are 5 sections of the Earth we're going to cover in this chapter, but we're going to spend most of our time at the outer reaches. Now, the 5 sections of the Earth are the atmosphere, the hydrosphere, the crust, the mantle, and the core. And we're going to spend most of our time in module 6 in the crust, in the outer reaches of the mantle, quite frankly, again, what we call the lithosphere. So again, if you look at this diagram here, we've got the crust on the outer edge of the Earth, 0 to 35 kilometers deep. The lithosphere is the next layer down. It's a combination of the base of the crust, the start of the mantle, 35 to 100 kilometers down. The asthenosphere, 100 to 700 kilometers. And then we get directly into the mantle, 700 to 2890 in kilometers. Our outer core, so the core is comprised of two components. The outer core, 2890 to 510 or 5100 kilometers deep, and then the inner core is our deepest section of the Earth as we know it. As we know it, again, obviously, some of this is speculation, some of this is just our understanding. Here again, we have a cross section. I need to move my little screen of me. There we go. Again, we have a cross section. The atmosphere outside of the Earth, we have our oceans, which would be part of the hydrosphere we talked about last week. If you look down the left side of this screen, you have the crust, 3 to 5 miles deep. The mantle consists mostly of ultramafic siliconates. Again, our mantle is a semi-solid, like a plastic rock, like we talked about last week. And then we have our core, the outer core, and the inner core. Now, if we go to the right side of the screen there, the lithosphere is both the crust and the upper part of the mantle. And so that upper part of the mantle is going to be mostly solid. It is, but it is movable. That is where our continental sheets and our plates are part of that lithosphere. The asthenosphere is partially molten, a little more plastic under pressure and fluid, going down to 700 kilometers. The lower mantle, more rigid, because of the pressure, and then the outer sphere and the inner sphere. Notice that the separation, we're going to come back to this, the separation between the outer core and the inner core, we call that the Lyman discontinuity. Notice that it's right in the center of the pie, right at the tip, the Lyman discontinuity. So again, what is the lithosphere? It is the crust in the upper mantle. It is solid. It is made of soil, sediment, and rock. In fact, lithos means rock. The asthenosphere, which is below the lithosphere, is that first plastic portion of the mantle, liquid rock due to pressure and temperature, or what we would call plastic, as we learned last time. Also notice a word here called the MOHO, the Mohorovic discontinuity, and that discontinuity exists between our lithosphere and asthenosphere. That's where the MOHO, or the Mohorovic discontinuity exists. So the MOHO on this screen is that red line. The red line between the crust and the lithosphere, or the crust and the mantle more specifically. It is part of the lithosphere. So if you look at the word mantle on the right side of the screen, underneath the word lithosphere, you can see how the mantle goes up to the MOHO and down until we get to the core. So the MOHO separates in the lithosphere, the crust and the mantle. Understand that one? Got it. All right. Let's talk about some definitions in this chapter. The Earth's crust is the Earth's outermost layer. Sediment is a small, solid fragment of rock and other material that are carried away and deposited by wind, water, or ice. Sand, mud, and gravel are all examples of sediment. Sedimentary rock is rock formed when chemical reactions cement solid sediment together, hardening them. Igneous rock is rock that forms when from molten rock, magma or lava in active volcanoes. And metamorphic rock is sedimentary or igneous rock that is transformed by temperature or pressure. I need to pause this for 1 second. Okay, I'm back. Hopefully that worked out. Had to let the dog in. Oliver was outside. So you guys have all met Oliver. Let's see, resume slideshow. There we go. Okay. Hopefully that transition worked out okay. We'll find out at the end. And plastic rock, rock that behaves like something between liquid and solid rock. Okay. What haven't we discussed from this one? Oh, let's talk about more discontinuities. So there's 3 discontinuities we want to talk about in this chapter. Again, the MOHO, the Mohorovic discontinuity, existing in the lithosphere between the crust and the outer, or the upper mantle, the outer mantle anyway. The Gutenberg discontinuity is between the mantle and the core, and the Lehman discontinuity between the outer core and inner core. So again, 3 discontinuities that I want you to pay attention to. Again, if we work our way down from the outside in, we have the Mohorovicek discontinuity, or the MOHO. That is between the crust and the mantle, but it includes, it's part of the lithosphere, separating the crust and the mantle. We have the upper mantle, the lower mantle. The Gutenberg discontinuity is between the mantle and the core, and the Lehman discontinuity is between the outer core and the inner core. Key points there. All right, let's talk a little bit about Earth's magnetic field. The Earth is a magnet. It has a north pole and a south pole. It has magnetic tendencies. The magnetic pole does vary in degrees from the geographic North Pole. So in other words, the points at which our Earth spin does not line up with the magnetic North Pole. So if I used a compass and it pointed me north, I would not end up at the tip of the Earth where its central axis of spin existed. It's slightly off, and it actually is moving. That magnetic North Pole is moving. In the case currently, it's moving actually towards Siberia, towards Russia right now, interestingly enough, at a relatively fast pace for something like this. Now, there are 2 theories, and you'll read this in your textbook, of why our Earth is magnetic. We tried to mimic this particular version in lab last week when we wrapped a nail in electric wire, and then we added an electric current to it using a battery. And that's the dynamo theory. A dynamo theory is a fluid motion of the outer core due to Earth's rotation plus core temperature differences. And that fluid motion of the outer core creates an electrical current. Notice the way that current is shaped on the schematic here, and how it mimics what we tried to accomplish with that nail and the electric current. So the inner core is solid, but that outer core is liquid. And because the Earth rotates, it creates fluid motion, and that fluid motion of molten metal in the inner core creates an electric current that creates a magnetic polarity in the Earth. That's the theory called the dynamo theory. The alternative to that is called the rapid decay theory. And that theory simply states that the Earth's electrical current is a consequence of how it was created, and due to resistance, it's actually slowing down. What's curious is we know that it's changing the magnetic field. And so this theory has some validities to it. We can see the schematic here of how the magnetic field also may protect us to a degree from the radiation of the sun. It definitely holds some water, but we don't know which one is right at this point. Okay, moving on to plate tectonics. What does plate tectonics mean? Well, we know the Earth is made of multiple plates, large land masses underneath the oceans that can shift and change, slide up against one another, underneath edges underneath one another. And so on this screen, you can see a number of the plates. So let's start by looking at North America, where the United States is. The North American plate is bordered by a number of plates. The Pacific plate, Smaller plates, Juan de Fuego, the Cocos Plate, the Caribbean Plate, the South American Plate, the African Plate, the Eurasian Plate, all border the North American Plate. In fact, so does, yeah, the Eurasian Plate, for that matter, borders it on two sides, because the North American Plate, as you can see, extends all the way into Russia. The Filipino Plate borders the Eurasian and the Pacific Plate, the Australian, Indian, the Arabian Plate. Then we have the Antarctic and Scotian Plate on the bottom of our planet. Now, there are 4 types of plate boundaries. We have a separation, collision, subduction, and sliding. This is on page 146 in your textbook. I would suggest opening to that, figure 6.4. So separation plates, you'll see in the upper right-hand corner of this screen where the plates are moving away from each other. It allows for parts of our mantle to move up onto the Earth. That's where we get volcanic eruption or lava, igneous rock moving up. Collision plates directly below it, where 2 plates are colliding together, is where mountain ranges form. Subduction plates, as we move to the left of the collision plates, where 1 plate is moving up, the other one down. In a subduction plate, very often the down moving plate can slide under the up moving plate. And sliding plates, where they are actually sliding against each other, and that friction can cause, well, it can cause quite a lot of damage, quite frankly. Now, plate tectonics are based on, or I should say, Pangea is based on the idea of plate tectonics. And that is that at one point in the history of this Earth, all of the land masses existed together in one giant mass called Pangea. Now, one question you may ask yourself is this biblical? And the answer is, we don't know. In theory, it makes sense. If at the beginning of time there was a singular place, in the Bible we call it the Garden of Eden, we could make sense of that singular place being Pangea, somewhere in the center. And over time, not only could that idea of the Garden of Eden being on Pangea be sensical in our timeline, but it also could make sense as to how and why there is a singular creation of animals and we see similarities on different land masses. So we can make sense of the idea of Pangea. We can make sense of even the movement, the sudden and quick movement of these plates, causing some significant natural issues on the Earth. In fact, if the continents that were Pangea shifted away from each other quickly, that could actually be part of the cause of a worldwide flood. It's within reason. What's not within reason, biblically speaking, is the timeline that you see on this screen. This is the timeline that secular scientists use to describe how the continents moved over the course of history. They're using millions of years. And our timeline in the biblical world doesn't span that. So therefore, we would have to reject the timeline here, but we don't have to reject the idea that it happened. It would just have happened at a different timeline, much faster. And quite frankly, that faster timeline would have led to catastrophe, like we see around the time of Noah's flood. So we don't have to reject Pangea as Christians. The idea that there was at one time a large landmass and all of the Earth's continents came from it. But the timeline in which they suggest Pangea happened does not fit our biblical worldview. Here's another look at part of Pangea that includes Africa, South America, India, Antarctica, and Australia. And there's evidence that Pangea existed because there is a similar fossil record for a number of fossils across the continents that makes it seem as if a number of these creatures lived at the same time in the same region. We have a handful of reptiles, some plants. So it's not, we have some evidence that Pangea was a thing, is what it comes down to. All right, now speaking of plates moving apart, earthquakes are a big part of that. An earthquake is a vibration of the earth that happens as a result of either volcanic activity or rock masses suddenly moving along a fault line. And a fault is the boundary between two sections of rock that can move relative to one another. The focus is the point at which the earthquake begins, and the epicenter is the point on the surface of the earth directly above an earthquake's focus. So notice that the focus does not happen on the surface of the earth. That's the epicenter. The epicenter is the point on the surface of the earth. 1 second. I'm back. Oliver was in the room. He wanted out. Happens during class too. Moving on. Now, here's another theory called the elastic rebound theory. You can look on page 149 in your textbook for this, figure 6.6. And what happens during the elastic rebound theory, again, notice the movement of the rocks here. We're talking about a sliding fault. Forces along faults push land masses relative to each other. So a sliding fault is a great example. As the land masses try to move, friction causes them to bend in response to the forces. That's the middle picture here on the screen. So we have forces moving in opposition to one another. As those land masses try to move, friction stops some of the movement and causes a bend. And eventually the masses break free of that friction. They return to their original shape, but not their original alignment. So if we had a wall along that fault line, that friction would lead to a shift in position of that wall, where we would suddenly have a separation between the two pieces of wall. That is the elastic rebound theory. And we can see that in places like the San Andreas Fault in California. One of the more famous fault lines in America, the San Andreas Fault, definitely shows evidence of the elastic rebound theory, such as the pictures on the screen. Now, fault lines and plate tectonics lead to mountains, according to our current theories anyway. We have 4 types of mountains exhibited on the screen. We have folded mountains, we have fault block mountains, volcanoes, and domed mountains, which would be an upwarped mountain range. Folded mountains are examples of the Appalachians and the Alps, where faults collide and the land masses fold up. Fault block mountains What we have is subduction, where one fault line moves up, the other one moves down, the Sierra Nevada mountains and the Grand Tetons. Volcanoes, Mount St. Helens, Kilimanjaro are examples of that. Domed mountains, the Zuni Mountains of New Mexico would be examples of domed mountains. Now the Rocky Mountains, I would have to assume, would be folded mountains as well, simply because of their shape and structure, but maybe they're fault blocks. I don't know. I should look into that. I'll let you know. So again, folded mountains, upwarped or domed, our fault block mountains, and our volcanoes. I would say the Rocky Mountains are definitely fault block, actually. I can't imagine that they're folded or upwarped. That takes us to the end of Module 6. We'll continue class December 1st, talking about weather. Again, please check out experiment 6.1, do it at home this week. We did the majority of the other experiments in class last week, so we'll cover all those Module 6 experiments. Everyone have a happy Thanksgiving. I look forward to seeing you on Tuesday, December 1st. Have a great day. Bye-bye.